I'm going to be giving the last talk. The idea is to provide a quick overview of Kalman filters. How many of you know how to derive Kalman filters? How many of you have heard of Kalman filters? Good. You remember the Chinese proverb? Come on, guys. You hear, you forget. You read, you remember. You do, you understand. We are going to do it. All of you? I'm going to start with some basic premise, some of the fundamental ingredients that make up what Kalman filter is all about. So let me quickly state them as basic results. Then I would like to dispel the notion, oh gosh, this guy can't use PowerPoint, so I want to say I can also use PowerPoint. One of the students asked me, are you going to use PowerPoint? He was surprised. So let me start with this basic fundamental problem. Let us suppose there is an unknown quantity x. There are two pieces of independent information about that, x1, x2. The mean of x1 is m. The variance of x1 is sigma 1 square. The mean of x2 is m. The variance of x2 is sigma 2 square. I'm assuming these two are two independent information. My aim is to be able to estimate the unknown x. So x is an unknown. There are two pieces of information I got. Both are random variables. They have the same mean but different variance. Given this setup, what is the best way to estimate x? So the word of estimation, so if you look at the set of all estimators, there is a class of estimates which is called linear estimates. Outside of this class is nonlinear estimates. There's a class of estimates that's called unbiased estimate. Unbiased is a statistical concept. So this intersection contains the so-called linear unbiased estimate. In general, we are interested in an estimate called BLUE, the best linear unbiased estimate. The best linear unbiased estimate sits in this intersection. It is a fundamental problem in basic estimation theory. Given a set of data about an unknown, how do you estimate the unknown? So you are given a data, you have to create an estimator. An estimator is a function of the given data. That function could be a linear function or a nonlinear function. The estimate could be a biased estimate, unbiased estimate. So we are interested in linear unbiased estimate. We are interested in the best linear unbiased estimate. There's a fundamental theorem called Gauss-Markov theorem. Yes, this is the famous Gauss. It's also a famous Markov. To me, I look at it as one of the foundation stones of the estimation theory. What does it say? Let us pretend there are two estimates. One is the least square estimate of the unknown x. Another is any other estimate. This is linear unbiased. This is also a linear unbiased. So what does the Markov theorem say? The Markov theorem says as follows, Gauss-Markov theorem. The covariance of the least square estimate is no greater than the covariance of x hat. So this is a matrix inequality. In principle, this could be a vector. I have if I can estimate the covariance of the estimate, the least square estimate is the best among all possible linear unbiased estimate. So it's one of the most fundamental and enduring theorems in least square in estimation theory. The Kalman filtering technique is well grounded in this notion of Gauss-Markov theorem, namely BLUE. After having stated it, I'm not going to prove it. We have proof of these things in our book, chapter 13, 14, 15. I'm now going to look at the structure of the Kalman estimator. We have seen several times repeatedly when you say Kalman, there's a particular form we assume. I'm going to show where that form comes from, why that particular form is a meaningful form. It has its starting right at this stage. So let us pretend that I'm going to get an estimator. I'm going to get a linear estimator, A1 plus A2 x2, that is going to be an estimate of this x. So x1 is the data, x2 is the data. This is the linear combination of x1 and x2. It's the linear estimate. So I am already in here. All of it in my place? I'll try. Now I would like to be in this intersection. So I would like to force it to be unbiased. So how am I going to make it unbiased? Let us take the expectation. So this is equal to A1 times E of x1 plus A2 times E of x2. If this were to be unbiased, this must be M. If this is already M plus A2, this is already M. I'm assuming my M is non-zero, cancels, so A1 plus A2 is equal to 1. So what does it mean? In order that this estimate, as a linear estimate, is an unbiased estimate, the sum of the coefficients must be 1. So what does this mean? This, as a linear estimate, must be a convex combination of these two data sets. All of it, me? Now I'm going to show you one more little thing. So let's keep this condition. Let us compute the variance of x hat. The variance of x hat is equal to E of A1 x1 plus A2 x2 minus, I have to subtract the expected value of this, which is equal to A1 m plus A2 m whole square. You all know that, right? It comes from basic formula for that. I can collect these two terms, I can collect these two terms. Also remember x1 and x2 are independent. So this gives rise to A1 x1 minus m plus A2 x2 minus m square. This is a plus b whole square. The cross term is 0 because I assumed independence. So this is going to be equal to A1 square E of x1 minus m square. I'm trying to do this simple arithmetic for those of you who have not done to be able to get familiar with. So this is A1 sigma 1 square plus A2 sigma 2 square, A1 square sigma 2 square. So I already have one condition on A1 and A2. So that forces the estimate to be unbiased. Now what is it I would like to be able to do? Find the A. So if A1 plus A2 is 1, there's only one independent parameter. Let's say A1. A2 is A1 minus A1. Find the A1 such that the variance of x hat is a minimum. A, I'm trying to find the best. I have ensured the possibility of it being linear and unbiased. Best in what sense? Minimal variance. So what do I now need to do? I need to be able to differentiate this quantity A1. So what is that going to be? That's going to be 2 A1 sigma 1 square. This is equal to 1 minus A1 squared. So this will be a plus 1 minus 2 times A1 minus 1 sigma 2 squared. I'm just trying to differentiate this with respect to and set it to 0. 2 gets cancelled. 2 gets cancelled. So what does this become? This becomes A1 is equal to sigma 2 squared divided by sigma 1 squared plus sigma 2 squared. Therefore, what is A2? A2 is going to be sigma 2 squared divided by sigma 1 squared plus sigma 2 squared. How many of us me? That's right. So that essentially tells you I have now computed, I have forced it to be blue. So what is the variance of of x hat. This is equal to the variance of x hat. I have to substitute in here. A1 is sigma 2 squared by sigma 1 squared. So A1 squared is equal to sigma 2 squared divided by sigma 1 squared plus sigma 2 squared whole square sigma 1 squared plus sigma 1 squared by sigma 1 squared plus sigma 2 squared whole square sigma 2 squared. So I can rewrite this as sigma 1 squared sigma 2 squared divided by sigma 1 squared plus sigma 2 squared whole square times sigma 1 squared plus sigma 2 squared, that is equal to sigma 1 squared sigma 2 squared by sigma 1 squared plus sigma 2 squared. This is a very fundamental relation. So in other words, I know the mean of my estimate, it is m. I also know the variance of this, and what's one more? This variance, the variance of x hat is equal to sigma 1 squared sigma 2 squared sigma 1 squared plus sigma 2 squared is less than sigma 1 squared, is also less than sigma 2 squared. It's a very simple algebra to check. So what does this mean? This variance is less than the minimum of sigma 1 squared sigma 2 squared. Are you with me? So what does it mean? Individually, x1 and x2 have variance of sigma 1 squared sigma 2 squared. The linear combination has a variance which is less than the minimum of the two. So when do I say I have a better estimate? The variance is less. Okay, now let's bring in data assimilation. x1 may be my background. x2 may be my observation. Why do we need to do data assimilation? If I have a background and a new observation, if I combine them in the blue way, the resulting estimate is better than either of the two data. So why do we do data assimilation? Hey, here's the reason. By combining, I can reduce uncertainty in a very particular way. And this is what happens in the Bayesian setup. I could redo these things in the Bayesian setup. So I simply did it in the standard least square way. All of it, me? So this is probably a PhD question. If you go for an oral exam, tell me why you should do data assimilation. Why do you combine? Why the combination is better than either of the information. Are you all with me? Okay. This is the first. Are there any questions on this? I'm going to do one more, and then I'll jump to let us come back to our old notation. Z is equal to hx plus v. X is an unknown. I have information about x in the form of z. I would like to have a linear estimator. Okay, before I go further, I would like to tell one more extension of this Gauss-Markov theorem. So least square estimate is best among all the linear estimate. So what does it mean? That could exist some nonlinear estimates whose variance could be less than the linear estimate. But finding such nonlinear estimators is a difficult problem. There is no recipe for finding better nonlinear estimators. You just have to do it trial and error. But there's one more extension of that. What does it say? If the noise associated with all the information is Gaussian, the least square estimate is the best among all estimators, including linear and nonlinear. That theorem is called Rao-Blackwell theorem. Rao after C.R. Rao. So what is Rao-Blackwell theorem tells you? Least square estimate is the best among all possible estimators if the underlying noise is Gaussian. So Gauss-Markov theorem, Rao-Blackwell theorem. These are two of the two fundamental building stones of estimation theory. Okay, now I'm coming back to the estimate. I'm interested in linear, so let me assume this to be k times z. What is me? I want my estimator to be a linear function of the, well, it's not strictly linear, it's an affine function, b plus kz. How many of those me? That's right. I first want my, so one of the things in here. I want this to be, this is already a linear estimate. I want this to be unbiased. So E of x hat is equal to m is equal to b plus k times E of z. So I'm taking expectations. I want this to be unbiased. I know x is a random variable whose mean is m. Z, so from this equation I get k times E of z. But what is E of z? E of z is equal to h times m, because E of v is 0. What are the properties of noise? I assume v sigma square. How many of you with me? Good. So what is this going to be? This is going to be h bhx. So yam, so hm comes in here. This is yam. So yam I combine. So I minus kh times m is equal to b. So there are two unknown parameters, k and b. By requiring the estimate to be unbiased, I have a constraint on b hat. Just like the constraint I had, a1 plus a2 is equal to 1. That's a constraint that comes from requiring the estimate be unbiased. How many of you with me? So I substitute this in here. If I did that, my x hat is equal to b I minus kh times m plus kz, which I can rewrite as m plus k times z minus hm. You know with me? That's right. So if you have two pieces of information, a prior and a posterior, a prior and an observation, a conditional information, you are going to concoct a form for the linear estimate. The linear estimate has this form, and this form, where does this come from? This is what the Kalman, this is what embodies the structure of Kalman filters. And where does this come from? This comes from a very simple requirement that I want my estimator to be unbiased. Much like I minimize the variance there, what is the problem in Kalman filter? Now that I have gotten rid of B, I still have K sitting around. I need to be able to find what the best possible way K is going to be. So what is the standard problem in Kalman filter? Find the matrix K such that X hat is a minimum variance estimate. And that's going to be the arithmetic in application of the estimation principles, and that's what I'm going to switch over. I'm going to show the arithmetic of computing optimal K that constitutes one of the defining equations in Kalman filters, the linear Kalman filters. That's what I'm going to switch over. Are you with me? So how do we combine the two information? When do you require unbiased? So you want to have two control. One, you want to make it unbiased. Another, you want to be minimum variance. If you want to induce two properties, you need two free parameters. In that case, A1 and A2. In that case, B and K. You all have an aha here? Good. Let's switch over to the standard Kalman filter equations. I know I would have liked to have done it on the blackboard. There's a lot more material. I need to keep writing, and that will be boring for you, so I'm going to do things. So this is based on chapter 27. Okay. So this is model dynamics in discrete time. If the model is nonlinear, I have a nonlinear map. If the model is linear, I have metric times a vector. The model is not perfect. The model has error. I'm going to, we have been talking about this. If I know the model error, I would have corrected it. I don't know the model error. I'm going to assume the model error is captured by a white noise sequence. Is it a good assumption? Well, if you give me something different, I will use it. But I'm going to get started by using this assumption. So if I know how to handle the arithmetic under this, if this assumption does not hold good, you need to walk a path. But slightly more complicated, but I can do that. So I'm going to provide you a trail of thought process leading to the derivation of Kalman filters. So xk is the true state, wk is the model error, xk is an Rn, m is a map from Rn to Rn. If it's a linear model, it's a matrix. Observations, we have seen it several times over this is probably good to see this. Zk is equal to h of xk if the observation is nonlinear. This is the linear case. This is a function from Rm to Rn. This is a function Rmn. Vk must be Rm. Sorry, that's an error. The mean 0, the covariance is Rk. Standard assumption. Even though I have done the linear nonlinear side by side, I'm simply going to be working with linear discrete time. So now you can see I can do continuous time, linear discrete time. I can have model linear, observation linear, model linear, observation nonlinear, and the two other combination, model nonlinear, this is nonlinear or linear. With me? So you have several branches if you want to be able to look at various scope for the derivation and analysis. Okay? So we have been talking about filtering, smoothing, and so on. I would like to be able to make this formal definition. I think it was in 1942, Kolmogorov and Wiener independently, they wrote papers which are similar, identical interpolation, extrapolation, and smoothing of stationary time series. In 1942, Wiener was interested with analyzing signals from radar to be able to detect whether the received signal is the reflected signal from an enemy aircraft or not. Are you there? Hey, Pearl Harbor has happened. They didn't want to be caught off guard. So they developed the radar technology to be able to detect whether the incoming aircraft can be detected. Who else but Wiener to be able to take that particular problem? So he essentially championed some of the early methods. In Wiener's time, there was no computer. So what is it they wanted? The electrical engineers wanted to be able to build a device. So you may have heard of Kalman filter, Wiener filter. Wiener filter is an electrical circuitry using passive elements. At that time, they didn't have software, computers, any such thing. They need to attach this device to the output of the radar, and it is that signal, the output of that filter, is the engineers are going to utilize to be able to detect whether it is a bird or a plane. So Wiener filter, Wiener was the champion of Fourier transform theory, so he used some of the more sophisticated techniques from Fourier transform theory, designed his filter. I'm not going to go into the details thereof. So what is the idea here? Given a collection of n observations, there should be a little I, there should be inequality. Please forgive me. Now you know why I'm doing the blackboard. My typing, I do like this. Okay, so given a set of data, if I am interested in estimating a state within this, so this is 1, this is n, k less than that, that's called smoothing. So when k is 0, that's the initial condition. That's why you remember Chris's talk, x now finding the initial condition is a smoothing problem. I'm going to utilize all the observation given to me to be able to decide what happened in the past. If I want to be able to estimate the state k at the time n, where the last observation is given, that's called filtering problem. If I want to be able to estimate a state which is where the subscript k is greater than n, that's called prediction. So what is one of the fundamental contributions? Smoothing, filtering, prediction are standard estimation problems from statistical theory. So that's the definition of the three classes of problems. So I have Kalman filter, I have Kalman smoother, I have Kalman predictor. You don't have to have Kalman predictor. In time series analysis, they have predictions. So predictive behavior means I would like to be able to extrapolate, which we all know. Okay. Now I'm going to state the problem with the linear case. So I'm talking about the linear discrete time dynamics. The initial condition is random. It is centered around mean m naught. The covariance is p naught. My dynamics is given by the standard equations. In some textbook they will use as wk. We prefer wk plus 1. So it's a matter of notation. This is the linear observation. So what is the problem? Given a bunch of n observation, find the best estimate xk of the estimate of the true state that minimizes the mean square error. this must be x hat of k. So what is that? X hat of k minus xk transpose x hat of k minus xk, expected value of that. That's what that one is. This is a scalar. So I can do mathematical jugglery and then show. Now let's look at this now. This is a scalar product. Here is a vector. This is the column vector. There's a row vector. There's an outer product matrix. Everybody in place? So this quantity inside the parenthesis outer product, expected value of the outer product, trace of that expected value outer product. So this quantity and the trace are essentially the same. But this quantity has a very nice interpretation as pk hat. What is that? That is the covariance of the estimate. The covariance matrix has diagonal elements, all variances. So this is the total variance. So minimize the mean square error, that is the variance. If x hat is an unbiased estimate, this mean square error is also become the minimum variance. So I want you to think about philosophically, there are lots of little things. Mean square error, minimum variance estimate. When do these become one and the same? The condition for that is the estimate must be unbiased. Bias means what? Well, the actual temperature is 72, but my thermometer is always reading plus 3 degrees. That's the bias. With me? Let's take into the problem. So I'm now going to talk about, so in order to do data assimilation, what is the need? We need two pieces of information at any given time. One of the two pieces is going to be obtained through the model by way of prediction. The other piece is going to be obtained by way of observation. I'm going to combine them. I have already shown you if I have two pieces of information, if I can combine them, if I combine them appropriately, I can have good characteristics. Yeah, your question? So at time 0, so I would like to initialize my filter. At time 0, f naught is the initial information that is given, all the information up to that time. So what is the best estimate for the initial state? The mean of this random variable, which is m naught. What is the covariance of that? That is p naught. These two are given to me. Even though I know the probability distribution for the initial state, I'm going to start the system with the mean. So given x naught, now my model, if I give this to my model, the model can pull it out. So x1 is the output of the model, and what is x1? x1 is equal to m times x naught 0 plus w1. So w1 is a random variable, so this is the random state. So I would like to be able to understand what is the predictable part of this. In order to find the predictable part of this, that's what's called the forecast. x1f, it is the conditional expectation of x1 given x naught. All of you, please? So this is naught, this is 1. I have this. My model is going to pull me out. I will get x1 from here. The model is going to be able to get this, but I won't know what w1 is. So I would like to get the x1f, which is the predictable part of that. That's called the forecast. So the forecast is simply the conditional expectation. x1 is x naught, m naught x naught plus w1. w1 is the mean zero noise. So that is equal to m naught x naught. Hat. How many others may? That's a prediction. Now, prediction has an error. So this is the true value. This is the predicted value. This is the error in prediction. I can substitute x1 is m of x naught. That comes from the true state. This is the predicted value. That is m of x naught hat. The predicted state has the noise, this one. So this is where I think I would like you to have a first aha. So how do I compute the prediction error? The prediction error E1f is equal to x1 minus x1f. What is this? This is equal to m of x naught plus w1 minus m of x naught hat. Are you with me? So this is equal to m of x naught minus x naught hat plus w1. So I would like you to think of what are the components of this error, the prediction error. One is the model error. Another is the error in the initial condition. This is the true. So the forecast error is a combination of the two. I'm able to move them forward. So the forecast error at time 1 is m naught times the forecast error, I'm sorry, the analysis error times 0 plus the model error. Now I'm going to compute. Please stop me if I'm not clear. Are me? So now I'm going to compute the covariance of the forecast error. This is again an outer product matrix. I know the expression from the previous. You do a little bit of matrix algebra, you get this. This is what that one is. This is a very standard form that comes in linear system. So what is that? So I'm now talking about no filters. I'm talking about stochastic dynamics. So let me quickly talk about that for a moment now. So if this is the initial distribution, if this is the mean of that, my model pulls it in here. This is the true state. This is the predicted state. All of it in place. So there is going to be a covariance coming from here. So if I call this covariance matrix in here, if I call this initial condition this, I would like to be able to predict. So this is so there are two things: dynamics of forecast and dynamics of forecast covariance. So the dynamics of forecast is simply m of x naught hat. Dynamics of forecast, if we did the algebra, what comes up in here? I would like to talk about this form for a moment. What is Q1? The covariance of the model noise. Okay, I would like you to look at those of you who you have to do this. There are 2 terms and 2 terms in here. If you multiply 2 and 2, you'll get 4 terms. Are you with me? But what are the tacit assumptions we are making? The assumptions are fundamental. I am assuming x naught is a random variable. I am assuming wk is a random variable. I am assuming vk as a random variable. So vk is the observation noise. Wk is the model noise. Xk is the random variable that talks about the uncertainty initial condition. What is the best thing to do to start with? All are independent. All are uncorrelated. Is it really true? I don't know, but I have to walk before I run. I want to understand the structure of the filter. Are you with me? That's right. That's the idea here. So if I understand, if you assume these are uncorrelated, if I multiply this with this, if I multiply this with this, are you with me? So only thing that survives, the product of this with this and the product of that with this. All the cross terms go to 0. So of the 4 term, 2 terms are cross term, they die, leaving behind this. Okay. How many of you may? If you know this, you know pretty much Kalman filter forecast plot. So now I would like to be able to tell why Kalman filter is expensive to implement. Let's talk about that for a moment in here, right here. My x belongs to Rn. So my PKF belongs to Rn by n because it is the forecast, it is the variance of the state. I have P naught hat. What is that? That also belongs to Rn by n. So this is the initial covariance. This is the predicted covariance. This is a n by n matrix. 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 So there are 2 matrix products involved. We saw a couple of days ago. This is O(n) cube. When n is when n is of the order of 1,000,000, we already found out it takes quite a few years. My life isn't enough to make 1 multiplication. Are you with me? Now I need 2 multiplication. How many of you may? That's the reason. It is not because we don't know how to do. I want you to understand one thing very fundamentally. It is meteorological systems are hard, not because we don't know how to do. Simply, the darn system is too big, and I don't have resources. So what do computer scientists do? I would like to be able to enable you to do these projects. So what are they looking at? Hey, can I increase the computing flops? Petaflop machine. Are you with me? Picaflop machines. So there are projects that are underway to be able to create machines that can deliver 10 to the power of 12 flops, 10 to the power of 15 flops. These projects are very exclusive projects. It costs millions and millions of dollars. computers that can realize this are essentially in experimental stages. Until such computers become a reality, we will have still difficult problems. What is the only thing you can do? You can simply increase the size of the problem as and when the computing power increases. So this is a very nice feedback between computer industry and the application industry. The application industry provides the impetus for the computer industry to be able to develop more and more and more and continuously larger computing powers. Okay, I'm not going to go there right now, but I want you to be able to recognize why we say Kalman filters are difficult to. So what is that we do? We do low rank approximation. So what is ensemble filters? It's a quick, simple way of approximating these matrices, not with full rank, but with decent low rank approximation. So one way of looking at all the developments in ensemble analysis, it's simply a way to be able to implement and approximate the full rank by low rank or reduced rank filters. Good. So with that, I can move in. I would like to be able to now do one more calculation. So what is the conditional observation given the state? You can see that is x1f. What is the covariance, the conditional covariance of the observation given the forecast? That is R1. That's very obvious, but it's good to do such arithmetic. Now I'm going to go forward. So I went from time 0 to 1. I can now take from time k minus 1 to k. So in meteorology, they use this particular terminology. So what is the idea here? So I have time k minus 1 and time k. So as a result of my pre-processing I got here, I also got p k minus 1. What does this embed? This embeds all the information that is contained in all the observations up to time k minus 1 plus the information for the model. In meteorology, they call this analysis. So if you look at the meteorology book, they will say xka, we simply put a hat. Then xkf, that's the forecast. So we use the hat for the analysis and the f for the forecast. So from here, if I apply the model, I get xkf. From here, if I apply the model, I get pkf. So what is xkf? Xkf is m times xk minus 1 hat. What is pkf? Pkf is equal to m times pk minus 1 hat, m transpose plus q k minus 1. Hey, the same thing that happened in here. 0 to 1, k minus 1 to k. So using these two, I create this pair from this pair. How many of us made? This is, so you have one model run, and this is equivalent to 2 model runs of every column of that. And that's where the expense comes in. Okay, suppose I got this. You are already bankrupt, right? Come on, guys. In reality, you are already bankrupt if n is a lot of. But then mathematically we can continue. So what is that now comes in? Yeah, new information comes in zk with rk. How many of us make here? Hey, we are in the same situation as we used to be. So I want to be able to now compute xk hat and pk hat by combining these two to get this. With me, I have a model forecast information, observation. I need to combine them to get this. Okay, there are at least 6 different ways in which you can derive Kalman filters. Some people claim there is more. Okay, I'm going to tell you a quick one. We already know. Hey, isn't this a 3D problem? So let me now talk about. So this is called the prediction phase. This is called the analysis phase. Prediction phase. This is called meteorologists call this an analysis phase. With me? So how do I create an analysis from these two? I can do it in several different ways. You already know why I'm going to mention this. Homework problem. Hey, you guys have to do this. So what is this? Concoct a j function, which is x, which is equal to 1/2 of x minus xk f pk f inverse transpose x minus xkf. Hey, this is the background term. How many of you are with me? xkf, pkf are the background information and its covariance. I'm going to concoct the background error term. I would like my x to be close to the background, not too far from the background. But I also have another information, 1/2 of z minus hf x, zk minus hf x transpose, rk inverse zk minus hf x. You remember in our second talk we talked about this? So this is the quadratic function of x, this is the quadratic function of x. Compute the gradient, sum them equal to 0. What is it you are left with? You are left with a system of linear equations. Okay? I'm going to quote the linear equation in a moment, but we all know how to do this. So that's one way. The second way would be to use the result I already talked about. What am I interested in? I'm interested in this. What do I have? I already have this. That's the background error. Kf. So what do I want? I want to be able to find a function kk such that this is zk minus hf xkf. That's a Kalman form. So what did Kalman say? Kalman said the following: after all, I'm interested in the linear unbiased estimate. I'm interested in the least square unbiased minimum variance estimate. I already showed you to start with. If I have two pieces of information, if I want to have a linear unbiased, the unbiasedness forces a structure under linearity to be of this type. In here, who are all the known? I know this, I know everybody. Who is the only one? kk. So what is kk? Kk is a knob. How am I going to use that knob? Is a control. I'm going to use this knob to be able to minimize the variance of this. Is already, this structure ensures that it's linear unbiased. I need to be able to induce it's also minimum variance. How many of you with me? I want you to look at, this is the very simple least square structure. This is the minimum variance linear estimation structure. Kalman in his 1961 paper used this structure. But later, once you understand it, there are several different ways in which you can do this. If you assume Bayesian, if you assume the distributions are Gaussian, that reduces to this. If you didn't have information about the distribution, this is simply a weighted least squares. So I have already talked about 3 different ways of doing it. No matter how you do, the end result is always the same. So you are going to get an expression for optimal x. You are going to get an expression for optimal kk. Do you see that? From a mathematical perspective, as a graduate student, you have to do these things. There is no way out of this. You have to have an aha. So this I have already done. I'm going to leave this as an assignment. I'm going to show you quickly the arithmetic relating to the determination of kk. So let me state the problem. My problem is as follows. Given the linear structure, find the Kalman gain such that the estimate has the minimum variance. How many of you have an aha here? Come on guys, nobody is moving. How many of you are with me? Last slide. So unbiased minimum variance, that these are the key vocabulary in the derivation of Kalman filters. I have already talked about this. This is a structure. This is the same structure in here. So I have already anticipated this. I'm simply showing the arithmetic of being able to compute the forecast error. So this is the model predicted part. We have already talked about that. Now this is the form. This form is exactly this. Prior innovation, Kalman gain. So what do I now need to do? You need to do a lot of algebra. So I would like to be able to relate xk hat with x hat k minus 1. So what do I now need to do? I need to substitute this in the model. I need to substitute this zk using here. I need to substitute this using this. So substitute, you get a huge expression, bulldoze. Are you with me? Quick matrix bulldozing. If you did that, substitute, simplify, you compute the error in the estimate. To be able to compute the covariance, you need to compute the error, right? That's right. I will make the slides available. I have slides, you already have the book. I have slides for several chapters from 13 through 28. I will make sure I give copies of all these slides to Amit, and you should be able to get copies of this. This is a quick summary of the different chapters. Now let's look at this term. I want you to look at this term and see where the things come from, where is the complexity coming from. Xk minus 1. Xk minus 1, x hat k minus 1, wk, vk. Look at this now. I'm carrying a lot of errors. So if I call this the error in the analysis at time k, the error in the analysis at time k is related through the model, the error in the analysis at time k minus 1. Good. One condition, one variance I want to talk about. Sometimes here where is that? Here I said yum. Could I call it mk? My model could be a constant model or it could be a time varying model. So what does it mean? Xk plus 1 is equal to yum xk plus wk plus 1 is equal to yum k xk plus wk plus 1. As far as arithmetic is concerned, there is really no difference except that instead of yum, I have to carry this mk through. So this is linear constant coefficient system. This is a linear time varying systems. Even though in some illustration I assumed a constant coefficient, everything the burden carries over. So that's why you have mk minus 1 and so on. So the expression that is fundamental in here is the following. So the analysis error at time k is related to the analysis error at time k minus 1 plus the model error plus the observation error. Are you with me? So this error term has three components. I have to compute the forecast covariance. So I need to be able to compute ek transpose. This ek hat has three terms. This will have three terms. 3 times 3 will be 9 terms. All the cross terms will die out because of my assumption. Now let us talk about some of those assumptions. So some of those things are not uncorrelated, they are correlated. What does it mean? Your expressions will be a little bit more complex. Can you handle this? Sure. Have you done this? Yes. We have done it in chapter 28. First, you need to see the beauty in the serene form. What do? You make all good things, all assumptions to make your life simple. All good things in life. You see the structure. Aha. Then try to release one of these. How does this complicate? How does this complicate? How does this complicate? That's the best way to learn, to see. So if you do arithmetic, I'm not going to do that. I'm sure you can do that. Look at this now. There are terms. Still you need to do a lot of algebra. So pk hat, if you did everything, you come in here, this is what I want you to concentrate. I'm going to concoct a quantity dk, which is hk. So what is hk? Again, I want you to remember, zk is equal to h of xk plus vk. Zk is equal to hk of xk plus vk. If it is h, my measuring instrument doesn't change in time. If I make it hk, my measuring instruments or measuring network changes in time. So I can assume the model to be invariant in time, the operator h to be invariant in time. Model can be varying in time. The model, the forward operator, this operator that maps the observation, that can also vary in time. So that's the general case. So I'm going to concoct a quantity dk to make life simple. Everything is known. Everything is known. So if you look at this, who is the unknown? Kk. So look at this now. It's the matrix. So this is the matrix. This is the matrix. Matrix, 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 everything. This is a quadratic term in kk. This is a linear term in the elements of kk. This is the linear term in the elements of kk. Yeah.
So, but how would we evaluate mk and nk?
Mk and Sk are supposed to be given, the model, the observation operator. If you don't give me, I don't come into play. That's a good question. Who specifies Mk? You need to give me several things. You need to give me my M naught. You need to give me P naught hat. You need to give me Mk. You need to give me Hk. You need to give me Qk. You need to give me Rk. So you are coming to me with a ton of data that describes the model. With me? And also you need to come with a sack of observation too. Okay, good. So the important thing I emphasize is that I would like to minimize the trace of this matrix. The trace of a sum is the sum of the traces. This trace of this quantity is going to be linear in the elements of K. This is going to be linear in the elements of K. This is going to be quadratic in the elements of K. So what do I now need to do? I need to be able to minimize the trace of this matrix with respect to individual elements of the K matrix. What is the K matrix? K matrix is a n by m matrix. N by m. So there are mn elements I need to decide. It's an optimization problem. I can do this optimization problem using standard quadratic optimization. You remember the Julia Child lecture I talked about? I'm not going to do it. I'm going to present the result now. The idea is very simple. So conditions on the Kalman gain, minimization of the total variance. I have done it. I'm not showing you the details of that procedure. So what is the optimal form of the Kalman gain? The optimal form of the Kalman gain is this: PKF HK transpose times HK PKF HK transpose plus RK inverse. Are you with me? Hey, we have solved the filter now. Why? I now know who this guy is. Once this guy is known, I do the analysis. So I use the model to forecast. I use the 3D or LAC scheme or the linear variance scheme to be able to compute KK. With me? Come on, guys. Do that. Now, before I go there, I would like to be able to give you two sets of expressions for you to look at, and there is a very nice duality between the expressions that you will get from here, and that's what's called observation space computation versus state space computation. So I'm now going to show that result, which is absolutely. So I would like to show the duality. Can I have that book for a minute? We have in a table form. This is table duality between two forms. When n is less than m, when n is greater than m. So P in here is equal to I'll come back to the notation in a minute. H transpose H sigma x H transpose plus sigma V inverse H sigma x inverse. In here, sigma estimate is equal to H transpose sigma V inverse plus H plus sigma x inverse. So let me talk about this notation. The notations are essentially my PKF is sigma x inverse over sigma V is my R, sigma x is equal to PKF. Okay. How many of you remember the matrix inversion lemma we talked about? Sherman, Morrison, Woodbury formula when we talked about sequential deterministic estimation. You remember that? So right here. So this I do in n is less than m. So what does it mean? This is called state phase formulation. state space. This is called observation space formulation. Observation space formulation. So I will implement the Kalman filter in the observation space formulation is m is less than n. I will implement the Kalman filter in the state space when n is less than n. This comes from Bayesian 3D VAR setup. This comes from linear minimum variance estimation. So there is a nice duality between the two. In other words, for every way of estimating using Bayesian or 3D VAR, there is a corresponding version. And how do you build a bridge between the two? Matrix inversion. So the recognition of this duality enables you not to pick one particular form for Kalman filter implementation, but to have two equivalent ways of doing it, depending on the value of m and n. Are you with me? I may not have told you all the details, but if any one of you is interested in the details, I can sit with you probably after lunch and talk about that. So now I'll show you several different slides quickly to show various ways in which I can. What is this? HAT is analysis. F is forecast. So the analysis covariance is essentially given by the matrix times the forecast covariance. You can also rewrite this in this particular form. There are so many beautiful ways in which this can be written. Now I'm going to give you a very simple interpretation. Let us take a case where m is equal to n and hk is equal to I. That corresponds to the Lenny's model this morning. He is able to observe the state. Hk is I means what? My observation is essentially the state. That's what that means. So in this case, pkf becomes diagonal. Let's also assume if pkf is diagonal, rk is diagonal. You compute the Kalman gain and you substitute this in here. If you look at the ith component of the analysis at time k, this is the ith component of the forecast at time k, this is the ith component of the observation at time k. Look at this now, RI, PK, II plus this. What is this? This is the covariance of the observation, this is the covariance of the forecast. Does this look like the one that I did a minute ago? Sigma 1 square by sigma 2 1 square plus sigma 2 square x1 plus sigma 2 square sigma 1 square plus sigma 2 square x2, that is equal to x hat. How many of me? I'm able to reproduce that result component wise. So Kalman filter makes sense. Kalman filter specializes to some of the most intuitive principles in estimation. I'm sorry, I hate to go like this. That's why I like the blackboard. But there are just too many things to do. Forgive me if I'm going a little too fast. One of the other thing I want you to remember is the following. I should have said PK. PKF. So what is the formula for that? If I'm going to be concerned with the model forecast, I don't need any observation. So what does it say? The model forecast. In other words, if I don't have any observation, what is PK? This is MK, PK minus 1 F MK transpose plus QK. So if I have a stochastic dynamics where I don't have any data, I'm simply pulling the model state. And if I'm going to be talking about the covariance evolution, this is the dynamics of covariance evolution. Look at this now. This doesn't require any observation. That's one of the things I talked about. And then we specialize lots of little things. If I don't have observation, what happens? If I have observations with, let me talk about one more special case before I go further. Sorry. Then I have no dynamics. My MK is I, WK is 0, QK is 0. It becomes 3D VAR problem. Are you with me? You want to be able to check the consistency of the derivation by specializing into several cases. Okay, this is another very important case. I'm going to discuss this for a moment now. Suppose the observations are perfect. RK is 0. RK arrives in here. RK determines my Kalman gain. So what is this matrix? So let us look at that matrix. HK, PK hat, HK transpose plus RK inverse. So this is m by n. This is n by n. This is n by m. So this whole matrix is a m by n matrix. This is a m by m matrix. We generally assume the observational error covariance is symmetric and positive definite. If this is symmetric and positive definite, the inverse exists and unique. Suppose the observation is perfect, this guy is absent. Inverse of this may not exist. All of it in place, it becomes an ill-conditioned problem. This is exactly what happens in ensemble Kalman filter. Remember Tony talked about inflating the variance? That's right. If the observations are too pure, perfect. RK is extremely small. If RK is going to be extremely small, mathematically you will have difficulty. So what do they do in ensemble Kalman filters? They create problems by having small number of samples, and then things don't converge. And what do? They hand wave and inflate it. And what is that is being inflated? They are trying to make this larger. If you make this larger, the inverse tend to exist. Your filter needs the filter will go forward nicely. Otherwise, it will probably die along the way. So when the observations are perfect, the filter will have problem. The filter will lead to divergence. How many of you have heard of filter divergence? So filter divergence could happen either because of numerical computation. I want to tell you quickly. In the 60s, Kalman did this in 61. They built an 8-bit machine on Apollo. The first time it was implemented on an 8-bit machine for tracking the spacecraft going to the moon. There are a lot of errors. The errors got to accumulate. How do they, well, at that technology, they couldn't afford to have more than 8-bit machines. So how do you make use of the 8-bit machine yet control the growth of other errors? What did they discover? They discovered the so-called square root filters. Square root, so instead of trying to work these things in terms of the covariance matrix, you update its square root. Why? The condition number for the square root is square of the condition number for the original matrix. It is the large values of the condition number that led to the numerical instability. So they were trying to control the numerical stability by rewriting the filter in what's called full rank square root filter. I'm sure many of you may have heard, and the reasons are right here when the observations are perfect. These are fundamentally important special cases one needs to remember. Well, I'm simply talking about this. So when RK is small, this will cause computational instability, could lead to divergence. Residual checking. Now, how do you know your filter is working correct or everything is good? You get this. This is called innovation. It can be shown that the covariance of the innovation is given by this. Arithmetic, mathematically. So what do you do? You compute the innovations and calculate empirically the covariance of the innovation. You assume ergodic assumption. The time average is equal to spatial average. So if you compute the covariance of the time series innovations, and if that matrix is close to this, I know everything in here, then your filter is working well. And you have access to this innovation because the filter adds the innovation every time. So you have access to this by doing an extra computation on the side. One can check whether the filter is working correctly. These are some sidekicks. Computational cost. I'm going to quickly go through this. So if I have a matrix in here, if I have a vector, to compute the model update, I need to do 2n squared. N is the size of the state vector. To be able to compute the forecast covariance from the analysis covariance using this, I need two matrix multiply and a matrix add, the 4n cubed plus 2n squared. To be able to compute the Kalman gain itself, you need 4n squared m plus m squared. To be able to compute the inverse, you need 1/3 of m cubed. So this is the inverse of a symmetric positive definite matrix. Under the assumption the RK is symmetric and positive definite, you use Cholesky-like decomposition that gives rise to 1/3 m cubed. then you need to be able to compute the matrix, which is the analysis covariance that takes this much. So the total cost comes like this. It is because of this expression you need to see that m is n. When m is less than n, when n is less than n, you do it here. When n is less than n, you do it here. It is this. It is a computational count like this helps you to be able to recognize the duality and be able to exploit that duality between the observation space and the model space. Okay, these are a few more. So this is the analysis covariance matrix. If you want to be able to compute the analysis covariance matrix, you have to shell out this much money. And so I have itemized all kinds of costs in here. For examples, I don't know how much of this I need to go through. How much time we have? Okay. So let us assume scalar dynamics, no observations. This is called stochastic dynamics. So this is a very simple linear system. Very simple linear system. I can solve this by back substituting. I can compute the covariance of this. Now look at the equation that describes the evolution here. Pk is equal to a squared pk minus n plus q. Pk is equal to that quantity. I'm going to show you quickly several things. So for a given m naught, p naught, q, I want to be able to compute the behavior of the moment. I'm assuming linear dynamics. In this case, my a, if a is greater than 1, the dynamics are unstable. If a is less than 1, the dynamic is stable. If a is equal to 1, it becomes a random walk under the assumption that this is a mean zero white noise process. So Xk will represent a white noise, a random walk on the integers. So I talk about the stable case, unstable case. In each of these cases, we compute the asymptotic values of the model covariance. In the case of random walk, the covariance at time k is equal to initial covariance plus k times q. Q is the covariance of the model noise. Now I'm bringing in observation, Kalman filtering. So I have explicit form of the Kalman filter for the linear case. Pedagogically, even though you may say, hey, I'm going to be working in a $1 million system, I'm sorry, not $1 million system, million by million size systems, you need to do this to get that final points of life. So we have given all the basic calculations in here. Homework number 1. I'm not going to go over that. You can see that. Okay, good. Now I would like to be able to talk about pk plus 1. Pk plus 1 is the forecast covariance. The forecast covariance is a nonlinear dynamics. Even for a simple linear scalar case, I want you to recognize that. That may not have come out very clearly in here. I would like you to bring it in here. This kinds of, do you see the place? Pk plus 1 is equal to a squared pk plus 1 over, divided by h squared pk plus 1 plus q, which must be a q in here. So this is a nonlinear difference equation. It is the Riccati version of the discrete time equation. So the covariance essentially evolves according to a nonlinear first order scalar difference equation, which is of the kind Riccati, which is a standard form in mathematics. It is an example of nonlinear equations. So now I'm considering very many special cases. What happens if h is equal to 1? Then I'm computing the asymptotic values, equilibrium. In other words, I would like to be able to find out where does the dynamics of the forecast covariance, analysis covariance get attracted to. Is there an attractor? That means, are they going to assume a stable value? All of it may. Hey, if you have a differential equation, what are the standard questions you ask? Does the solution explode? Does the solution come down to 0? Does the solution oscillate? Does the solution exhibit chaotic behavior? Until 1963, the only thing we believed in either explodes, comes down to 0, oscillates. Lorentz in 1963 added a new vocabulary called chaos. So what is chaos? To me, chaos is like an energetic tiger in a cage. That's it. There is so much energy, it keeps going around, but it can't go to infinity. Chaos is a form of instability happening in a finite dimension, in a finite subspace. An unstable system confined to be in a finite subspace, what does that have to do? It's unstable, so it has to keep moving. But the finite dimensional, the finite box it has to remain, what does it do? It folds itself. So one way to think of chaos is an energetic tiger confined to a cage. You can see a tiger, right? So if you attach a pen to the tiger's body, you know what I'm talking about. So you need to be able to analyze the asymptotic behavior of these quantities. So it's an attractor to a repeller. Then we would like to be able to see how fast it converges. We would like to be able to compute the rate of convergence. I know I'm going very fast, but I want you to know we can do all these things. This is the analysis of convergence of a Riccati equation. It's a very standard, but mathematics is nice. Okay, so analysis of covariance convergence. Then another way you can talk about is that what happens to the errors. The difference equation that talks about the evolution of covariances, they are all deterministic difference equation. But if you consider the evolution of the forecast error, this is the stochastic difference equation. How many of you are me? That's right. This is the stochastic part, that's the stochastic part. So this is the homogeneous part of that. So you need to be able to understand the solutions of this stochastic dynamics. It's a very interesting exercise mathematically. Well, that's the end of the show. So in summary, I'm not going to go into the nonlinear part. So in summary, before I'm in k minus 1. I go to k. I get x hat, k hat. I pull it. I'm sorry, k minus 1. I pull it xkf, pkf. You give me zk, rk. I'm going to create x hat, pk hat. Is responsible for this part. This is the minimum variance estimation. Are you with me? Come on, guys. You see the filter equations now? That's right. The filter equations comes in here. The filter equations is very simple. Xk hat is equal to xkf plus kk zk minus hk xkf. We know how to design this. And that's the quick summary of Kalman filters. Now, what are the things now? I would like to go to, if you want to go to nonlinear, where is the difficulty? I'm going to tell the difficulty of nonlinear problem at a mathematical level. So you need to understand, you may have a big problem, but you need to be able to model that big problem in a small way so that we can understand. So what is the challenge in nonlinear filters? Suppose x is a random variable. Suppose x is a random variable with a known mean and sigma square. Let us also throw in the fact that it's random. Normal. Suppose g is a function from R to R. I'm simply talking about scalar, and g is a nonlinear function. So let the distribution of px be normal. In basic statistics, if g is a function of x, I can compute its distribution, pg of pg. Come on, guys. How many of you have done basic probability theory? How many of you know that given x a random variable, its distribution, g is a function, gx is a new random variable, how to compute the distribution of the function of a random variable? It's a standard formula. Probability theory talks about that. Okay. Now, what is it I want? I would like to be able to compute the mean of gx. I would like to be able to compute the variance of g of x. So what is mean of gx? Mean of gx is going to be equal to integral g of x P of x x dx minus infinity to plus infinity. What is variance of g of x? Variance of g of x is equal to integral minus infinity plus infinity g of x minus e of x square p of x x d of x. Are you with me? The largely difficulty is that for a general nonlinear function, there is no closed form in which we can compute variance. In other words, the variance of a nonlinear function in general is difficult to compute. So what do? You approximate. How do you approximate? You express g of x in a Taylor series. If you take the first order term, you get the first order approximation. If you take the second order term, you get the second order approximation. And that's largely the problem. So what is extended Kalman filter? Extended Kalman filter is the filtering equations obtained by approximating the variance of a nonlinear function by the first order term in the Taylor series. Are you with me? So what is the shape it is going to take? Let me quickly. So this is where the problem lies. You should be able to pin down where the problem lies. So in the case of nonlinear filter, what is that? Pk plus 1 f is approximately equal to. So what is the nonlinear model? Xk plus 1 is equal to m of xk plus wk plus 1. This is the nonlinear model. How does this vary? This is the Jacobian of m at xkf pk f Jacobian of m xkf transpose plus qk plus 1. All of it in place? I can never compute this covariance precisely. I can only approximate. I can approximate to the first order term. I can approximate to the second order term. If you approximate to the first order term, you get first order filter. What is first order filter? That's called extended Kalman filter. You can get second order filter. We have derivations of all those first order filter, second order filter in chapter 29. I'm not going to go into the details. But then I want you to know that it's 1/3 of a semester course. So what I have done, if you want to do it in all details, going every place where it takes you, is probably 5-6 lectures. All of you? So if some of you thought that I went a little too fast, I'm totally with you. If I were on the other side, I would feel the same way. But why did I do what I did? This is the last lecture I wanted to bring and give a little big picture without spending too much time on the calculations to provide you an aha value. So how many of you now got an aha value? That's right. I know you have to do the work, but I know where to go. I'll now be happy to take some questions. So what are the variations in here? If the model is nonlinear, if the observation function is nonlinear, approximation, first order filter, second order filter, then you can talk about. Okay, now let's look at one more. Even though this is an approximation, this is an n by n matrix, this is n by n matrix. Who has money to compute this? Then I have to throw this out and compute a low rank approximation. So approximation on the top of approximation on the top of approximations. That's the way of life. Then this is all going on. So let me also tell you historically something. Kalman did this in 1961. Kalman was famous within the meteorological community because of the filter, but in control theory community, Kalman is famous because of several different things. You remember, did you talk about observability? So Kalman was the pioneer. Controllability, observability, reachability, stability, realizability. It was at Courant Institute. Steve Cohen and I think Mike Gill. Mike Gill was his advisor. So the first entry into the world of meteorology came around with a thesis of Stephen Cohen. He's at NASA now. He used to be a student at Courant. And what was the evaluation? He applied this to shallow water model. He pretty much concluded Kalman filter and meteorology, they don't go together. That was essentially the conclusion because of the curse of dimensionality. Then that promoted the geophysical researchers to think about various different ways of approximation, reduced rank filters, square root filters, all these were well understood. Then came the ensemble idea. Why ensemble is popular? You don't have to write a single line of code. If you have model code, you can implement ensemble. Are you with me? Pretty much. Few statistics here and there. So ensemble filters became very popular because it's a very good reduced rank approximation. So if you have million by million, if you have a system of size million, if you took 50 ensembles, you are having hopefully at most 50 rank approximation to a million by million matrix. Are you with me? Okay, now I want to tell you a couple of things now. We talked about principal component analysis. Amit talked about approximating the dog by picking singular values. There the approximation, he picked it. You took 5, you took 10, you took 20, and so on and so forth. Are you with me? So you could play with it because the problem is simple. Do you know anybody in ensemble forecasting has used 500 ensemble on real world model? I haven't seen yet. At Oklahoma, there's a lot of work in ensemble going on. Yeah, you have done it? Okay. Oh, you know of something. Okay. In Oklahoma, there's a lot of work in radar assimilation. Most of the ensembles, if you talk to them, I'm using 50. How good is it? Oh, I'm satisfied. It's good. Works well. What criterion? Oh, it works well. Are you with me? Why? Even 50 ensemble is expensive. We have a supercomputer which is available and free all the time, and they gather 95% of the time. That's right. So, are you with me? So the ensemble Kalman came in the 90s. I'm talking about historically. So there are competing ideas, particle filters. There is also another ensemble approximation called uncentered filters. Uncentered filters. Uncentered filters is a careful approximation of the ensemble. This is the deterministic ensemble as opposed to the stochastic ensemble. So if you pick the deterministic ensemble in an appropriate way, I can compute the covariance to a second order accuracy. That's what that one does. The Evanson's ensemble filters as well as the uncentered filters, they came nearly the same time. Nearly the same time. Oliver? Any other questions? Again, I apologize if I know I've gone fast. Well, lunch is not ready?
No, it is.
Okay. Then what are we waiting for? Thank you. Thank you.